one of the most important mathematical tools for a physicist is the idea of eigenvectors of a matrix. Eigenvectors are a really cool topic. They're really important. They come up all over the place in physics, everywhere from mechanical systems to quantum mechanics to rotational dynamics. They're everywhere. And I want to spend a few minutes just talking about the math of it, how to deal with these things. If you've ever taken a class in matrices and linear algebra, at least when I took a class in matrices and linear algebra, I went through and there were lots of techniques for manipulating matrices in row-reduced form and all this stuff. And then suddenly we talk about eigenvectors and it's, oh my gosh, that's awesome! And so I want to share a little bit of how they work and what they are with you. This first video, all I want to do is just say what an eigenvector is. Not how to find them, but just what it is and a hint or two of what they're useful for. To do that, let me start by just talking about the gist of it. I'll give the definition, then we'll do some examples to talk through what it looks like. So the definition is that if I have a square matrix, an m by n matrix M, and a column vector, an n by 1 matrix V, and a scalar, an ordinary number, lambda, could be a real or a complex number, if I have those, and the matrix multiplication of m times V gives the same result as just lambda times V, just a number times the matrix, times that vector. Matrix times vector is just a scaled version, stretched or compressed version of the same vector. If you get that, that is called an eigenvector. V is an eigenvector of the matrix M, and its associated eigenvalue is lambda. So that is the idea of what an eigenvector is, and that seems very abstract. So let me just do some concrete examples. First concrete example, let me make my matrix M. I'm going to define it to be the following matrix. I want to do 4, minus 1, 3, 0. That's my matrix M. And I want to consider a handful of different vectors that I can use in all this. Let me do a handful of vectors. So for example, let me say the vector V is the vector 1, 3. This is a 2 by 2 matrix and a 2 by 1 matrix, so I can multiply them. I find that 4 minus 1, 3, 0, matrix multiplied times 1, 3 gives me 4 times 1 plus negative 1 times 3 is 4 minus 3. That gives me 1. And 3 times 1 plus 0 times 3 gives me 3. That's 1 times V. And so what I find here is that this has an eigenvalue. This is an eigenvector with lambda equals 1. I've shown that it's an eigenvector by doing mv equals this and saying it's a multiple of my original vector. Great. Okay. Another vector I could consider, let me write down u equals, just to give another vector here, u equals 1, 1 as my vector. And forgive me, by the way, my 6-year-old daughter drew this lovely fish on my board, and I'm working around it because I think it's cute. So, okay, if u is my 1, 1 vector, let me do the matrix multiplication. 4 minus 1, 3, 0 times 1, 1. And what will that give me? 4 times 1 plus negative 1 times 1 is 4 minus 1 is 3. And 3 times 1 plus 0 times 1 is 3. That's 3 times the vector 1, 1. So its eigenvalue is 3. These are both eigenvectors of my matrix. They're eigenvectors of my matrix, and right now this seems very strange. Okay, that's cool. Just to point out, not every vector is going to do this, right? If I were to define the vector w, okay. If I were to find the vector w to be, I was going to say w is, let's do 1 minus 1 as my vector w, and let's try what that matrix multiplication does. 4 minus 1, 3, 0 times the vector 1 minus 1 gives me, that's 4, 4 plus minus 1 times minus 1 is 1, that gives me 5, and 3 times 1 plus 5, 3, and that's not equal to a number times 1 minus 1. If it were 5 minus 5 it would be, but here it's not. It doesn't fit that mold. So this is not an eigenvector. I hope it's clear that most vectors are not going to be eigenvectors of this matrix. it has to, in general, it's kind of a cool coincidence when it works out to be an eigenvector, to have those properties. And in fact, we can look into this a little bit and say, what vectors will be eigenvectors in this matrix? Well, okay, so 1, 3 is an eigenvector, and maybe you can believe me if I tell you that 2, 6 would be an eigenvector. Let's look. 4 minus 1, 3, 0 times the vector 2, 6 will give me 4 times 2 is 8, minus 6 is 2, 3 times 2 is 6, plus 0 is 6. That's 1 times 2, 6. So it's got the eigenvector 1 again. And again, you can see it's the same thing. In fact, any multiple of 1, 3, of the vector 1, 3, will have the same eigenvalue 1. So as soon as I found one eigenvector, any multiple of that eigenvector will have the same eigenvalue. You can kind of see that by factoring it out, right? If this were, if I said 2 times v here and 2 times v there, numbers, scalars, factor right through matrix multiplication. So it doesn't really matter if I stretch or shrink v, it'll have the same properties. So in some sense, it's the direction of v that matters, not anything about exactly how long v is, what its scale is. Same thing with u. The vector minus 3 would come out to be minus 9, the same eigenvalue 3 if I did this. Now that's how eigenvalues and eigenvectors work. We find the specific eigenvectors for our matrix, and each one has its eigenvalue, but most vectors won't be eigenvectors. Something that's kind of cool though, it turns out, if you look at this, our W up here, our W was equal to, if you look at it, 1 minus 1 is equal to 2 copies of U minus 1 copy of V, right? 2 times my U was 1, 1 minus 1 copy 1, 3. That will give me 2 minus 1 is 1, and 2 minus 3 is minus 1. That'll give me my W up there. And this is kind of a cool thing. It turns out that m times w, we already saw m times w was not an eigenvector, but that's equal to m times 2u minus v, and that's equal to 2mu minus mv, right? I'm just doing algebra here. Algebra works with matrices. And hey, mu, I know what that is. That's 2 times u had eigenvalue 3, 3 times u, minus mv had eigenvalue 1, 1 times v, so that's 6 times u, 6 times my u vector was 1, 1, minus 1 copy of v, 1, 3, that's 6 minus 1 is 5, and 6 minus 3 is 3. I get the same result this way. So this is actually a hint of why eigenvectors are useful even if most vectors are not eigenvectors. It turns out that especially in cases where you have in linear algebra terms, a basis of eigenvectors, enough eigenvectors that you can make any other vector out of them. If you have an n-dimensional space, you need n eigenvectors, and that's often true in the matrices we work with in physics. We'll see why later. But if that's true, then you can take any vector you have, write it as a combination, a linear combination of those eigenvectors, and then instead of doing any matrix multiplications at all, you just replace those with their eigenvalue things, with their eigenvalue times vector, and you just do some ordinary vector addition, or vector linear combinations at least. You never have to do that full matrix multiplication. We'll eventually learn in physics applications of this, where that's a really powerful and useful property to be able to take a general vector and write it as a sum of these eigenvectors. It turns out to be really powerful. So this is one example of eigenvectors. Let me do just a couple other examples of this to illustrate that as we go along. So I'll clear some space here. Clearing space, not clearing the fish. Clearing space. Another example I wanted to look at. Let me do the matrix 2 minus 1, 6 minus 3 as my matrix. That's my M this time. And I want to tell you that I've got two eigenvectors for this as well. The two eigenvectors I would say for this, one of them is going to be 2 minus 1, 6 minus 3 times, and one of these eigenvectors is going to be the vector 1, 2. What's that give me if I multiply by the vector 1, 2? Well, I get 2 times 1 plus minus 1 times 2. That's 2 minus 2, or 0. And down here, 6 times 1 plus minus 3 times 2, that's also 0. That's equal to 0 times 1, 2. So my eigenvector, my eigenvalue for this is 0. The vector 1, 2 has eigenvalue 0. That's allowed. We can't have the vector be 0. That wouldn't be reasonable. But its eigenvalue can certainly be 0. This is a vector where matrix multiplication just kills it, throws it away. The other eigenvector for this, by the way, 2 minus 1, 6 minus 3, those are commas, sort of. The other eigenvector that this particular matrix has is 1, negative 3. And if we plug that in, we'll find that gives me 1 times 2 plus 3 is 5, and 6 times 1 plus 3 times 3, that's going to be, wait, am I happy about this? I'm not happy about this, am I? 2 times 1 plus 2 times 3 is 5, and this other one is, I'm getting 6 plus 9 is 15, and I'm worried. That doesn't work, does it? Why did I think this was going to work? Oh, because it's supposed to be, yes, cool. Because what I actually meant to write here was minus 6, 3. Sorry, minus 6, 3. And if I had done that, this still works properly. It still comes out to 0. But down here, I'll get 5 and 15 this time, or minus 15 this time, because negative 6 times 1 plus 3 times negative 3 gives me negative 15. Sorry for the changing my matrix there. 1 minus 3, that's what we come up with. And so this is equal to 5 times 1 minus 3. So the eigenvalue here is 5. That's another example of a matrix and its eigenvalues that shows, or a matrix with its eigenvectors and eigenvalues that we can see where 0 is a perfectly fine eigenvalue to have. These are all, I've done 2 by 2 matrices here just because they're easy to do the math. They're quick and easy to do. But let me take just a second and look at a slightly larger matrix, just to do one example of a larger matrix and talk a little bit about what comes up there, because there's some interesting things that can happen when you have larger matrices, or that are more interesting with larger matrices anyway. So one of those things we can look at is we can say what if our matrix M is, and let me get down the exact matrix I want. So I want minus 3, 5, 2. It's going to be a 3 by 3 matrix. 1, 1, 2, 0, 0, minus 4. That's my matrix. 0, 0, minus 4. And let's look at a few vectors that I will tell you are eigenvectors. I just want to show you how these eigenvectors work. So, for example, one of the eigenvectors of this matrix turns out to be, I'll call it U is 1, 1, 0. 1, 1, 0. And let's check that out. M times U is going to be minus 3, 5, 2, 1, 1, 2, 0, 0, minus 4. I'm going to go through this multiplication pretty quickly. You can check it yourself. You pause the video, check it yourself to follow along at home. But just to do this quickly, 1, 1, 0, rather than boring you completely with me doing multiplication, I get minus 3 plus 5. Minus 3 plus 5 plus 0 is 2. I get 1, 2, 1 plus 1 plus 0 is 2, and I get 0, 0, 0, 0. So that's 2 times this, so lambda equals 2 is the eigenvalue for this particular vector. I will say that V is going to be the vector, and let me see what I did for this one. 2, 0, 1 is going to be my vector. Let me do a matrix multiplication for this one to test it out. Minus 3, 5, 2, 1, 1, 2, 0, 0, minus 4 times 2, 0, 1. When I multiply that out, I'll do the matrix multiplication. I get minus 6 plus 0 plus 2 gives me minus 4. Is that what I expect? Hang on. That's minus 6. Double checking that I have this doing what I want. Oh, darn it. I knew I'd make this mistake. Minus 3, 5, minus 2. That didn't change my earlier result because there was a 0 in the last place, which is why I didn't catch it. Okay, yeah, that's better. So that's minus 6 plus 0 minus 2 is minus 8. Okay, sorry for the minus sign error, but it'll work here. So got that. Then 2 plus 0 plus 2 is 4. Oh, wait, no. 2. Did I have a minus sign here that I missed as well? My goodness, those were both supposed to be minus 2s. And again, that was all in the last space, so I missed it. sorry. So 2 plus 0 minus 2 is 0. And 0, 0 minus 4 here. So the lambda, the eigenvalue for this one, is going to be minus 4. I get a minus 4 eigenvalue for this. And then I'll go ahead and do one more vector. For a n by n matrix, you can have as many as n eigenvalues, or as many as n eigenvectors. Sometimes you don't have that many, but you can have up to that many. And in this case, we do. Let's say vector w is, and again, I wrote this down, minus 1, 1, 2. This I'm going to triple check my minus sign so I don't confuse you. Minus 1, 1, 2 is what I have written down. And let's check what that one gives me with matrix multiplication. Minus 3, 5, minus 2, 1, 1, minus 2, 0, 0, minus 4, times minus 1, 1, 2, gives me, that's 3, plus 5 is 8, minus 4 is 4, and this is negative 1, positive 1, I'm worried again, so minus 1 plus 1, 0, yeah, this is minus 4, and 0, 0, minus 8. Well, hey, that means this has lambda equals minus 4 as well. Minus 1 times minus 4, 1 times minus 4, 2 times minus 4. Okay, we've shown that this is also an eigenvector with eigenvalue minus 4. So we've got these three eigenvectors, but here's something kind of interesting. You remember before we saw that if we mixed two eigenvectors, or that if we mixed two different eigenvectors, we didn't get an eigenvector in general. It wouldn't be the same multiplication. It wouldn't give the same thing. It wouldn't. We added linear combinations of eigenvectors are in general not eigenvectors. Here's the fun part, though. Let's look at v and w. They have the same eigenvalue, the exact same eigenvalue, and what that means is that, for example, v plus w is, let's see. 2 minus 1 is 1, 0 plus 1 is 1, and 1 plus 2 is 3. 1, 1, 3 is v plus w. That's just adding those two together. Let me do a quick check here. Minus 3, 5, minus 2, 1, 1, minus 2, 0, 0, minus 4, times 1, 1, 3. When I multiply those, let me check it out. Bear with me. That's minus 3 plus 5 is 2, minus 6 is minus 4. That's 1, 2, minus 6 is minus 4. And that's 0, 0, minus 12. And that is, in fact, a lambda equals minus 4 again. So wait a minute. How many eigenvectors do I have? I said I can have up to n independent eigenvectors. Well, what's this mean? I now have 4 eigenvectors for this system. The trick is that anytime you have 2 eigenvectors with the same eigenvalue, then any linear combination of those 2 eigenvectors is going to give you another eigenvector. This is the sort of broadened version of saying that stretching and shrinking, and a single eigenvector will always give an eigenvector the same eigenvalue. It's the same thing, just stretched or shrunk, and it'll give the same result. Well, here, I guess linear combinations of one vector are just stretches and shrinks of that one vector. Here, I'm doing linear combinations of 2, and I get the same thing. I get a vector with the same eigenvalue. In technical terms, what we can say is that these 2 vectors span a space, an eigenspace of the eigenvalue minus 4, and any vector in the plane defined by 2, 0, 1 and minus 1, 1, 2 any vector in that plane will be an eigenvector of this system. You can actually argue it pretty quickly once you think about it. You can argue it, right? If I have, let's say I have vector u, v, w, let's say I have vector s equals a times v plus b times w, where a and b are constants, or just numbers. If I have this, and I do m times s, I can write that as m times a times v plus m times b times w, which is the same as a times mv plus b times mw. And mv and mw, they're eigenvalues. And they're eigenvectors, so they have the same, and they have the same eigenvalue. So this is a times lambda times v plus b lambda w for the same lambda for both of them because they're the same eigenvalue. And hey, that means I can factor stuff out. This is equal to lambda times av plus bw. So it's a quick proof, but it just shows you that any combination of two eigenvectors with the same lambda will also be an eigenvector. And that's what we've seen here. So in general, this is how eigenvectors work. This is what you do with them. I'll do another video eventually to talk about how to compute these, how to figure out what these matrices have for their eigenvalues and their eigenvectors. But for right now, I hope this is giving you an idea of how they work and how they behave. Just the first glimpses of what you do with these. For practical applications, take some physics classes. It's good stuff.